So this is going to be a lesson on 1.4, force due to gravity. Now, if you dropped, and the do not question here says, if you dropped a textbook and a piece of paper at the same height, would they fall at the same rate? Now, it doesn't have to be a textbook, right? You can do this at home. You can use a folder or any object as long as it can fit the piece of paper on top of it. So you're gonna drop it at the same height apart from one another. And if you drop both at the same height at the same time, you would see that, well, whatever object you're holding, like your folder, would drop at a faster rate than a piece of paper. But and that's something that's intuitive, right? You guys would all think that, you guys would all realize that, well, my textbook will, or rather your folder or whatever object you're dropping, drops at a faster rate than your piece of paper. But what if I placed that piece of paper on top of the textbook or your folder or whatever object you're using? And again, as a reminder, your object has to be able to, well, it has to be larger than your piece of paper so the piece of paper can fit entirely on that object. And if you do this yourselves properly at home, if you put that piece of paper on top of your folder or whatever, and you drop them, without holding onto the paper, mind you, right? Do not touch the paper at all when you're holding the object and getting ready to drop it. If you were to drop it properly, you would see that the textbook or folder and the piece of paper would drop at the same exact rate. They would fall down at the same exact rate, at the same exact time. And why, right? Why do you guys think so? Why is that the case? Why is that the case? And the reason why is because of air resistance. Now, I want you guys to, this is very important. This is a video that you guys should watch because it shows you that same exact principle, that same exact example we're trying to do now in this video. So pause this video, go to the Google Slides, watch the video, then come back to this one. Right, this is very important for students that were not in class before. Very important because that you want to actually see it happening. So assuming you watched the video, right? So assuming you watched that video before, here are your notes, right? You can clearly see that, well, the air atoms, when you do have air, the air's the paper hits all these air atoms and the paper slows down. It's the same concept as a parachute. Your parachute is hitting all that air, all those air atoms, and you're slowing down. But if you don't have any air, right? If there's, let's say you're in space on the moon, all objects drop at the same rate. If there is no air resistance, doesn't matter how light you are, doesn't matter what your weight is, every object drops at the same exact rate if there was no air. And this is true. This is something you guys have to get used to. All objects would drop at the same rate if there was no air. Weight has nothing to do with how fast something drops. The only reason why objects drop slower is because of air resistance. Objects do not drop faster because they weigh more. They drop slower because of air resistance. So what do you think is the difference between mass and weight? Mass is essentially just the amount of atoms that make you up, right? Because no matter where you go, if you are on the earth, the moon, the space, well, your mass would always be the same amount, right? I'm made up of the same atoms. I'm made up of the same stuff. It's the amount of space that an object takes up. So my mass is always the same. Weight, on the other hand, Weight, on the other hand, is the measure of, well, how strong is the force of gravity acting on you? How strong is that gravity, right? Because the Earth's gravity is way stronger than the moon's, which means that you would weigh a lot more on Earth than if you were on the moon, right? You would weigh a lot less on the moon. But your mass would always be the same. Your mass is essentially the amount of matter that makes you up. So you are always you no matter where you go. But your weight would change depending on the surface of whatever planet or celestial object that you are on. So the third formula that we're going to learn in this class is G is equal to Fg over m. G means gravitational field strength. In other words, that is also your acceleration due to gravity. That we can say that G is my acceleration due to gravity. Fg is my force due to gravity, and m is my mass. My acceleration due to gravity near Earth's surface is 9.8 newtons per kilogram, or meters per second squared. Right, that's how fast objects are being pulled near the surface of the Earth. 9.8 newtons per kilogram, or meters per second squared. And we use G to represent acceleration due to gravity, or the gravitational field strength. They both mean the same thing. So let's do our first practice problem. Right. So we have this. So a 60 kilogram physics student, right? So let's say our mass is 60 kilograms. And the 60 kilogram physics student would weigh 1,560 newtons on the surface of planet X. And the question says, well, what is the magnitude of your acceleration due to gravity, which is G, right, on the surface of planet X? So now you have this formula. G is equal to Fg over m. So Fg is 1,560, mass is 60, and you get somewhere around 26 meters per second squared, or 26 newtons per kilogram. Either unit works, either unit is fine, either unit is correct. All right, so we have the second question. A 2 kilogram object, is falling freely near Earth's surface. What is the magnitude of your gravitational force? And so they want to know what was your Fg, F sub G. There's something you can assume here. You're falling near the surface of the Earth, right? So you're falling near the surface of the Earth, which means that your acceleration due to gravity is, your acceleration due to gravity, G, is 9.8 meters per second squared. Which means, and this is something you have to assume if you're near the surface of the Earth, so G is equal to Fg over m. If you're, for example, orbiting Earth, your acceleration due to gravity would not be 9.8, but here, if you're near the surface of the Earth, it is 9.8. So G is 9.8, Fg over m, which is 2 times 2. So now you have 19.6 newtons is your force due to gravity. All right, so that's 4B. For C, so it says that you have a 65 kilogram astronaut, weighs 638 newtons on Earth. What is the mass of the astronaut? So they're looking for, well, what is the mass of this astronaut on the surface of the moon? Where your acceleration due to gravity is 1.6 meters per second squared. So there is no math involved in this question. The question is literally asking you what is the mass of the astronaut on the surface of the moon. You should realize that mass never changes. So the answer here, you're already given the answer. Your mass is 65 kilograms. Done. 240. On a small planet, astronaut uses a vertical force of 175 newtons. So he's applying a force of 175 newtons to lift an 87.5 kilogram boulder at constant velocity to a height of 0.350 meters. The height doesn't matter now. We'll talk about height later in unit 2. So the height doesn't matter. Sorry, so I'm not even gonna underline the height. But traveling at constant velocity, that is important. And the question then goes on to say, well, what is the magnitude of your gravitational field strength? So there's something really important here. And the something really important here is that if the question is saying that if you're traveling at constant velocity, well, that means your forces are balanced and your F net is 0. We talked about this in 1.2. Which means that if you're lifting something at constant velocity, right, and your net force is 0, then what is my force due to gravity here? What is that force due to gravity if my net force is 0? That must mean my force due to gravity is also 175. It's equal. My force due to gravity is a downward force. My force due to gravity is 175 newtons here. Because if I were to travel at constant velocity, these two numbers would have to be equal for my net force to be 0. Right? My net force is equal to my applied force plus my force due to gravity. If my net force is 0 here, then my force due to gravity has to be negative 175. Right, so 175 plus negative 175, 0, 0. My forces are balanced. Right, my forces are balanced here if I'm moving at constant velocity. All right, so now that we know that our force due to gravity is negative 175, right? So G is equal to Fg over M. Fg is negative 175. M is 87.5. So G is equal to negative 2 meters per second squared. Now, because the question is saying what's the magnitude, again, the magnitude is just the size or quantity of an object, meaning you don't care about direction. We're not going to care about this negative sign, right? And so our answer here is 2 meters per second squared. And that's our answer. For E, a rock is thrown straight up into the air. At the highest point of the rock's path, the magnitude of the net force acting on an object is what? Right? So you have a rock in the middle of nowhere up in the air. Ignoring air resistance, which we pretty much will always ignore, my force due to gravity is the only thing acting on the object. Right? So my net force here is my force due to gravity. And again, force due to gravity is another name for weight. rather, is another word, because I don't have enough room here. Force due to gravity is another name for weight. So if your net force is your force due to gravity, then your magnitude of net force is equal to literally the same as the magnitude of the rock's weight. All right.